Okay, Algebra 2, here we go with section 2.1, which is introducing two words that you may have heard before and maybe you don't remember, relations and functions. And these two things are going to be so elemental to everything we're going to do here throughout the course of the year, you're going to kind of forget about these words. Kind of like a fish doesn't really know what water is because it's everything that they do. That's the way we're going to be here with functions. So, relatively short section here. And we're going to just try to get a few basic vocabulary terms down before we get started. So the first word we're going to work on here is the word relation. And even more so than the word function, this is one you can deal with and not even really know it. A relation is simply defined as a set of ordered pairs. So eventually, we are going to be graphing a lot of relations and trying to figure out what they look like when we graph them, but that's basically it, our definition of a relation. And you'll see some examples of this later on, but really quickly, a set of ordered pairs. All right, so one ordered pair might be the ordered pair 1, 2, where 1 is your x-coordinate, and 2 is your y-coordinate. So that there is one ordered pair, and in a set, we would most likely have more than one. So I'm going to separate that with a comma, and then do another ordered pair, maybe the ordered pair 3, 4. That's a second ordered pair. And let's go ahead and put a third in there, and let's make the numbers a little bit more interesting. Maybe 0 is our x-coordinate, and then maybe we're going to introduce a negative number for a y-coordinate. So let's just quit right there. 3 ordered pairs, 1, 2, and 3, that's a relation, everybody. And when we're talking about a set in mathematics, we always use these curvy braces at the beginning and the end to indicate that that's where our set is. So what we have here in red is an example of a relation. 3 ordered pairs written together in set notation. All right, when we talk about the word domain, this is the second thing we're going to define right here. Relatively simple definition here. The domain is going to be the set of all x values in your relation. Set of all x values in a relation. So if we're going to stick with the same example that we came up with just before right here, we would say that we had in red that the domain of that particular relation that I had would be all of your x values. My first ordered pair right here had an x value of 1, so I'll start with that, comma. My second ordered pair, 3, 4, has an x value of 3, comma, and our third ordered pair, 0, -8, has an x value of 0. So we'll put 0 there, and since the domain is a set, we again are going to put braces at the beginning and at the end, and that's what a domain looks like. All of the x values in your relation are called your domain. All right, let's see if I can make this work here. Scrolling this up a little bit. Okay, all right, and moving on now, range is going to be the third word that we're going to define right here, and a range is going to be, let's jot this one down, if a domain is the set of all of your x values, the range then is going to be the set of all your y values. So basically the same definition right here, except now we're putting y in instead of x. So the set of all y values in a relation. And sticking with the same example here, our range would be, okay, we know that it's a set again, so I'm going to begin this with a brace, and we're looking at all of our y values. 1, 2, the first ordered pair, has a y value of 2. The second ordered pair, 3, 4, has a y value of 4. And the third ordered pair, 0, -8, has a y value of -8. And we'll close that with a brace, and that's what a range looks like. So, domain and range go hand in hand. Lucky for us, there's an easy way to remember which one is which, alphabetical order. Domain, D, comes before range with an R, and X comes before Y alphabetically. So that's one way I always keep those straight. Domain is X values, range is your Y values. Okay, so those are the first 3 vocabulary terms we had. The fourth one now is pretty important. This one here, function, as I said, is what we're going to spend 99% of our time working on here this year. And the definition of a function is going to be as followed. Now, let's not get too far ahead of ourselves. We begin with this idea right here. A function is a relation. However, we want to be a little bit more specific here. It's a relation in which, and here's where it becomes important now, each, and we'll simplify this. I don't think we need to use domain and range here. So we'll say each x value is paired with, you can use the word only, probably the word exactly though is better here. Each x value is paired with exactly one y value. All right, that's it as far as the definition goes. But that's one of those things you can write down and you can ask people, okay, do you get it? No, nobody really gets what a function is until you start to see a relation that is a function and a relation that's not a function. But if we go back to the one we were just working on, let's take a look at what we wrote down. I'll shrink that down so we can see everything all at once there. In our domain, we had the values of 1 and 3 and 0. The 1 right over here is paired with a y value of 2. The 3 right here, the second x value, is paired with a y value of 4. And 0, the third x value, is paired with a y value of negative 8. Each of those x values is paired with one and only one y value. So the relation that we wrote down here in this first example is a function because each x is paired with only one y. However, if I had done something different, if I had said that this x value here was a 1, don't change this in your notes, guys, I'll change it right back. Now we have a problem, and let's talk about why. The problem is right here and then right here, the first and third ordered pairs. The way I've changed it now, the first ordered pair has an x value of 1 paired with a y value of 2. The third ordered pair has the same x value again, 1, but now it's paired with a different y value of negative 8. And if the same x is ever lumped together with two different y values, you don't have a function anymore. It's still a relation, but not a function. But I'm going to undo everything right there. I didn't want to mess that up too much. All right, so let's keep it there. And that's our definition there of function. So now let's start to see this in action right here. All right, so what's going on here on our second part of our notes right here? We're going to let A represent a relation given here. And sometimes you'll see this written out, everybody, with a capital letter maybe in front of that. So we'll go ahead and try to do that. Capital A is equal to, all right, and what do we have? 1, 2, 3, 4 ordered pairs. They're all separated by commas, and there are braces at the beginning and braces at the end. So A is a set of ordered pairs, and that's the definition of a relation. We're going to talk about a few different ways of representing a relation. The first thing we're going to do in part A here is represent A with what is called a mapping diagram. Not expecting you guys to know what that means already, but we'll just kind of illustrate it quickly. We don't need to write a definition. It's not all that fancy. Here's what a mapping diagram looks like. Basically, you start with an oval here on the left, and then another oval over here on the right. And basically that first oval is going to represent your x values, and that second oval is going to represent your y's. And what we're essentially doing is writing the domain and range in each one of these two ovals. The domain, we said, is the set of all your x values. So as I look up at A here, at my 4 ordered pairs, the first x value we have is a 3, so I'll put a 3 there in that first little oval. The second x value we see is a negative 2, so I'll put that one there. Now, this is where it gets interesting. The third x value that I gave you here is 3, which we already have right there in our domain, and it is not necessary to write the same value twice within a mapping diagram. So I'm not going to write the 3 a second time. Then I'll go to my fourth ordered pair, negative 4, 5, and include the negative 4 for my third x value. And what we've basically done is written the domain of this relation. The domain, the set of all x values, is 3, negative 2, negative 4. So then you can probably guess that in the second oval, which we've labeled y, we're going to be putting our range, all of our y values. So we start off with a y value of 5. Now obviously I'm writing the 5 first because that's the first y value that I see, but there's no rule that says that you have to put these numbers in any particular order, so don't worry about that. My second y value is a 1. Third y value is a negative 7, and the fourth y value right here is 5, which we already have. So there's no need to write that 5 again, as we said earlier. So we've written our domain in the x bubble right here, 3, negative 2, negative 4. We've written our range here in the second oval, 5, 1, negative 7. And the only thing we have left to do here is draw arrows showing which x values get paired with which y values. So nice and simple. The first ordered pair, 3, negative 5, we're going to draw an arrow from the 3 in the domain to the 5 in the range. Second ordered pair, negative 2, 1. So we're going to draw an arrow that pairs negative 2 in the domain with 1 in the range. Third one, all right, something interesting happens now here. 3 gets paired with negative 7. Remember, we didn't write the 3 again, so we'll just draw an arrow that goes from the 3 to the negative 7. So now you start to get arrows pointing in different directions, and it gets a little bit more interesting. And the fourth and final ordered pair, negative 4, 5, is going to be an arrow from negative 4 in the domain to 5 in the range. So as I said, sometimes the arrows start moving in some different directions there, and things look maybe just a little bit more interesting. So that's what we call a mapping diagram. It's just one way, I should say a second way, of expressing the ordered pairs in a relation. The first way is what we had right over here, which is just the list. Okay, a third way we're going to do this now is representing a relation with a graph. I didn't put that in a great spot right there. Okay, so let's go with this. Maybe I'll make that a little bit bigger to see. And this is something you guys hopefully have done a lot of over the years, and you remember how to do it. We're just plotting ordered pairs here on this graph. So the first one we have here, 3, negative 5. And, not going to put anybody on the spot right here, but it is always kind of funny. Sometimes people get these numbers mixed up a little bit. Remember that in every ordered pair, the first number, which in this case is going to be 3, is your x-coordinate. And the x direction is always moving you either left or right. The second number, 5, is your y-coordinate, and that's always how far you're going to go up or down. So when we go to plot the ordered pair of 3, 5, probably need to make that a little smaller. There we go. 3, 5. We start at the origin, which is this point right here in the middle. I'm putting a dot there just so you can see it, but don't actually put a dot there in your notes, everybody. And this 3, 5 tells us that we are going to go 3 units to the right. So 1, 2, 3. You wouldn't put a dot here, but just so you can follow me. And then 5 units up. 1, 2, 3, 4, 5. So right there, everybody, that is the ordered pair of 3, 5. And now that I've done that, I'll go through and erase all the junk that I did to get there. I don't want to get you guys in the habit of putting those points there. So 3, 5 is our first ordered pair. Second ordered pair, negative 2, 1. Since our x-coordinate is negative 2, we start at the origin and we go 2 units to the left, which is right here, and our y-coordinate is positive 1. So we go up 1 unit and put a big dot right there, and that's the ordered pair of negative 2, 1. And again, I'll erase all the stuff that I did to get to that spot. Okay, hopefully this is ringing a bell now. Third ordered pair, 3, negative 7. So starting at the origin, I'm going to go 3 units to the right, 7 units down, and that's going to get us right here. We'll label that one too, 3, negative 7. It's not necessary that you guys label those points, but I'm just kind of doing that so you can get a sense for where things are right now. And our fourth and final ordered pair is negative 4, 5. Starting at the origin, we're going to go 4 units left, and then positive 5 means we're going to go 5 units up to this spot right over here, and I'll label that one as well, negative 4, 5. Now, what I'm hoping you notice right here, the original relation up at the top had 4 ordered pairs. Kind of like here in our mapping diagram, we had 4 arrows. And here in the graph right here, we have 1, 2, 3, 4 points, 4 ordered pairs that we're dealing with. Okay, couple of follow-up questions right now here, guys. 2 quick simple ones and one that's a little bit more complicated. State the domain of relation A. So the domain, we said, is going to be the set. So we're going to begin it with a brace of all of your x values. And the order in which we do that really doesn't matter at all, but I would imagine most of us would just look at the definition of the relation, which I have right up here. I've made a big mess out of this, and we're just going to list our x values in order, which we actually did already right here when we were coming up with our mapping diagram. So if you've done that, looking at the mapping might actually be the faster way to do this. The domain is the set of all of the x values, which are going to be 3, negative 2, and negative 4. And we'll end that with a brace. And remember, the 3 got used twice. Once right over here and once right over here, but there's no need to list it twice when we're writing out our domain. Part D is asking us for the range. So here we go. The range is the set of all of our y values. And to get that, I'm just going to look right over here in the mapping diagram, and I'm going to write them in the order I had them there: 5, 1, and negative 7. Just a reminder to everybody, the order in which you write your domain or your range doesn't matter. Some people like to go in numerical order, so they might have written the domain negative 4, negative 2, 3 from least to greatest, or the range might have been negative 7, 1, 5. Doesn't really matter. You're going to get full credit for that either way. And now finally the important question that I wanted to get here to, is relation A a function? So if we go back to our definition from a moment ago, which has disappeared on us, there it is. A function is a relation in which each x value is paired with exactly one y value. So now as we look back here at number 2, we're trying to find out here, and it's always easier to see if something is not a function first. Do you ever have one x value that's paired with 2 different y's? And the answer to that is going to be yes. Right over here, we have an x value of 3 paired with a y value of 5. And then in the third ordered pair, we see the exact same x value again, 3, but this time paired with a different y value of negative 7. We can see the same thing from the mapping diagram here. 3 is paired with 5, but 3 is also paired with negative 7. And when that happens, when the same x value is paired with 2 different y values, then the answer here is a big fat resounding no. Your relation is not a function if the same x is paired with different y values. So that is one nice problem right there that kind of puts everything together that we were working on this one as well. Okay, just a couple things right here to finish up here. Something interesting out there called the vertical line test is a quick way to look at a graph and see if you can determine if a particular relation is a function or not. I'm going to try to spread this out just a little bit more. And here's the way the vertical line test works. If you were to take the graph of a relation and draw a series of vertical lines on top of it. So let me call this example A here. I'm going to draw a whole bunch of vertical lines. I'm going to draw maybe about 5 of them, but of course there are more. Here's what's happening now. You'll notice that in what I just drew, each one of those 5 red vertical lines crosses the original graph once. There's a point of intersection here, but that's it for that vertical line. And the second one point of intersection. Third, 1 point. Fourth, 1 point. Fifth, 1 point. When you only have 1 or 0 points of intersection between your vertical lines in your graph, then your answer here for part A is that yes, this relation right here is a function, because we would say that this graph passes the vertical line test. But now, if we were to take a look at what I'll call example B, I only need to draw one vertical line here to show you that there's a problem. That vertical line that I just drew crosses this graph twice, once right there and once right there. And when that happens, you can very quickly say that no, your relation right there is not a function. And the quick reason why would come from, if we were to just kind of guess, the coordinates of those 2 ordered pairs. Now, I'm just eyeballing here, guys, but it looks like this ordered pair is maybe something in the neighborhood of like 2, 3. All right, I'm just going to go with that. Now, if this were a vertical line, though, that means that this second point of intersection is directly below the first one. Its x-coordinate would still be the same as it was initially, 2, but the y-coordinate now looks like it's going to be negative. Let me say that that one's maybe a negative 3. And what you might notice from there, the same x value of 2 is paired with 2 different y values of negative 3. That violates the definition of a function, so that's why we would have to say here that example B is not a function, because this graph fails the vertical line test. Let's look at a couple other ones here. I'll call this one example C. This is a shape here, guys, in blue that if you're not familiar with, you're going to get pretty familiar with before the end of the year. This is what's called a parabola. You may have dealt with that in Algebra 1, but I know 2 years ago you guys, you might not have seen it, and you might have forgotten it since then. You didn't see it at all last year in geometry. But if I were to do the same vertical line test, drawing a series of vertical lines over that graph, I'm just looking to see, do the vertical lines ever cross the graph more than once? And the answer is no. 1 point, 1 point, 1 point, 1 point, 1 point. So this one right here, yes, this one is a function because it passes the vertical line test. But then over here in example D, if we were to draw vertical lines over here, there are no points of intersection, and that's okay. If I drew a vertical line right here, the y-axis, that looks like there's 1 point of intersection. That's okay. But as soon as I draw a vertical line over here to the right, now I've got 1 and 2 points of intersection. And having even one vertical line with more than 1 point of intersection, that's a failure right there. So this graph here, no, it is not a function. D fails the vertical line test. So the vertical line test is a pretty quick way to look at a graph and figure out if your relation is a function. If I can actually go back a slide, everybody, to the graph that we just came up with here, let's take a look. I know this doesn't look exactly like the other graphs right here, but if I were to draw a vertical line right there and ask you guys, how many times does it cross the graph? The answer is once, right there at the point -4, 5. Likewise, if I drew this vertical line, it crosses the graph once. So no problem so far. If I were to draw a vertical line, let's say right here, that's no points of intersection. So that's fine too. The problem though is when I draw this vertical line right over here, and I ask you how many points of intersection there are between that vertical line and the graph, there's one here at 3, 5. There's another one right here at 3, -7. That's 2 points of intersection. That tells us, everybody, that this graph right here is not a function, which is just kind of verifying the answer that we came up with before when we looked at it in terms of the actual definition. So 2 different ways of looking at it, but we're getting the same answer both ways. Let me get rid of all of that junk. All right, and we are going to move on now to the last thing we're going to do in this section here, guys, and that is just to hopefully reacclimate you guys with something called function notation. So functions are what we've been talking about for a while here, and the word notation just means a way of writing things. So function notation is something that looks like this. And I'm going to go ahead and put a box around that. Now, I'm hoping you guys remember how to say that, but you might not. So let's take it from the top. F is the name of your function. X is the variable that we are using. And we would read that, everybody, with the words f of x. All right? And we would read this as f of x is equal to 3x minus 7. And that's just a set of directions that we're going to do with a function called f. No matter what our input value of x is, we take x, we multiply it by 3, and then we subtract 7 from that result. Okay? Now, in this same problem, there's another function that I gave you, and that one is right over here. So this one we would read as g of x. So whatever that letter is out in front, then you use the word of, and then the variable right there. G of x here is equal to x squared plus 1. So whatever x is, we're going to square that number, which of course means multiply it by itself, and then add 1 to the result. And of course, you have to pay attention to order of operations here, guys, although these two are pretty straightforward. So I'm going to ask you guys 4 quick questions right here, and I'm going to do 2 of them with you. At that point, you might want to pause and maybe try the second 2 on your own, but let's see what we got. Our first example here, A, we're asked to evaluate f of 4. Now, you'll notice I switched back to red. Because this is f, we're going to be using this function right over here. And with f of 4, well, here we go. The original function definition is 3x minus 7. So I'm going to write 3, but instead of the x, I'm going to put an empty set of parentheses and then a minus 7. And what number are we putting inside those parentheses? Where there used to be an x, there's now a 4. So where there was an x right here, we're going to replace that with a 4 in this one particular problem. So we're taking out all of the x's and we're replacing them all with 4s. Now, at this point, we could go back through the old PEMDAS that you guys learned a long time ago, probably back in middle school, and talk about order of operations. Parentheses, exponents, multiplication, division, addition, and subtraction. Although that's actually a little bit misleading the way that I did it, because multiplication and division really happen at the same time, and so do addition and subtraction. So the two operations we see here are multiplication between 3 and 4, and then a subtraction at the end, and we're going to do the multiplication first. Now, that being said, you guys got your calculators already. Your calculator, in fact, just about any calculator made in the last 30 years, has been programmed with an understanding of order of operations. So if you guys were to just type this expression into your calculator exactly the way it looks, including the parentheses, it would do order of operations correctly and give you the right answer. But I would like you guys to practice using your brains a little bit, so here we go. That 3 times 4 is going to give us a 12, and 12 minus 7 is going to be 5, and that is our answer to this question. F of 4 is equal to 5, meaning when you put a 4 into this expression here, 3 times 4 minus 7, you're going to get 5 for your result. Okay, second example, guys, g of 5. So now we're looking at this function right over here. So g of x was x squared minus 1. Everywhere there was an x, I like to put an empty set of parentheses temporarily. So something squared and then a plus 1 at the end of that. And what number are we putting in here? The x value in this example here is 5. So everywhere there was an x, we're going to put a 5 in there. So again, you can go to your calculator, type this in exactly the way it looks, but I think you guys can probably do this one in your head. 5 squared, exponents are going to come first. 5 squared is not 10, everybody. That means 5 times 5, which is 25. Add a 1 to that, and 26 is the answer to that question. G of 5 equals 26. Okay, moving right along right here. Third one I gave you, trying to scare you a little bit here, guys. Let's see if you fall for it or not. F of 7/3. Now, nobody likes fractions, but one of the things I'm going to try to work with you guys on this year is to get you to realize that maybe fractions aren't quite as scary as you thought in certain circumstances. So this is another F question, so I'm going to the F function right here, and it's going to be 3 times something minus 7. And the input value here is this fraction of 7/3. Now, I would expect just about every single one of you would go to your calculator right now and try to type that in. But what I'm hoping you might have noticed here, everybody, is that we're taking 3 here in red, multiplying it by the fraction 7/3. What this really means is 3 times 7 and then divided by 3. The cool thing that happens here, guys, is that this 3, which is really a numerator, and this 3, which is a denominator, they completely cancel each other out. So we really just end up with 7 minus 7, and the answer to that one is going to be 0. So F of 7/3 is equal to 0. You're welcome to use your calculator if you want there, but that little trick is something I'm going to work with you guys on throughout the course of the year. And I think I have one more for you here. There we go, g of -9. So I'm going to switch back to green because we're at the g function again, and g of x was something squared plus 1. And we're going to be putting a -9 right here in for our x value. Now, the reason I gave you guys this problem is because I was about to ask you to do it in your calculator, and this is one of those problems, it's ironic, people actually tend to do better on a problem like this when they do it by hand rather than when they use their calculator. So if you want real quick, go ahead and pause, put this into your calculator, and tell me what you get. Now, the answer that I hear a lot of people say here, if I've got this right, is -80. And that, unfortunately, you guys, is the wrong answer. I'll explain why in just a second. The correct answer here is going to be 82. You're going to take -9 first and square it, which means multiply by itself. -9 times -9 is positive 81, and then add a 1 to the result there, and you're going to get 82. Now, the reason that a lot of people get this wrong when they go to use their calculator, they don't put the parentheses in. So what happens a lot of times is people will type this in, -9 squared plus 1. And the calculator interprets that differently than the way you intended it. What your calculator reads this as is not -9 squared. It reads it as the opposite of 9 squared. So the calculator is going to do this first. 9 squared is 81. Then it's going to take the opposite of that result and make that -81 and add 1 at the end there and come up with -80. So the calculator isn't wrong, but you didn't tell the calculator exactly the way you wanted that interpreted, so that's why the calculator will give you a wrong answer. The big thing I want to warn you guys about right there, anytime this year you're taking a negative number to a power, you've got to remember to put parentheses around the base of that exponent. Not this. Doing this is really exactly the same thing wrong that I was doing right over here. The square needs to come outside of those parentheses, so it really needs to be -9, close the parentheses, and then square it. And that will get you the right answer of 82. Okay, guys, that's as much as I think we needed to go over for section 2.1, so let's give that homework a try and see how we do, and we'll come back and talk about that next time we're together.